We're going to actually try to prove a concept that I haven't even talked about in lecture yet, and that's conservation of momentum. This is the goal. You've probably heard this term somewhere before, conservation of momentum. But we have to understand what is momentum. It's a simple definition. It's just mass times velocity. So in physics, for some historical reasons, momentum is a vector, since it's a scalar times a vector velocity. And for some historical reasons, we represent that vector with a lowercase p. So it's momentum, but we use a little lowercase p. But it's defined as the mass of your object times its velocity. So it points in the same direction as the velocity, and it's just scaled by the scalar of the mass. You can see the units are kilograms, meters per second, whatever, it's kilograms, meters per second, but yeah, that's momentum. So if you have some object with some mass that's moving in some direction with a velocity, then the momentum points in that same direction. Okay, so why do we want to invent this new concept of momentum? How is that going to help us? It's going to help us solve physics problems with collision, which is something we haven't addressed yet in any of our physics problem solving. When you have a collision, for example, you have two objects that are crashing into each other, you don't have constant forces. You have forces that are changing over time. The two objects are not in contact with each other, so there's no force on each other. Then as they come in contact, there's a force that grows, and they're in contact for a short amount of time, but it's like a spiking force. Changes with time. And so you can't use kinematic equations, and you might not even know the functional form of the force. So it will be difficult to solve differential equations. But this concept of conservation of momentum is going to help us solve collision problems very easily. Let's see why. So imagine that we have two objects that are moving towards each other with some initial velocity. So here's mass 1. This is going to be very much like our experiment. Here's mass 2. Imagine they're on some frictionless surface. This guy's got an initial velocity, and this guy's got an initial velocity, and they're going to crash into each other. Okay, so if I did a free body diagram for this initial mass and this initial mass, if there's no friction and if they're moving at constant velocity, we know that the sum of the forces have to add up to equal to 0 if it's moving at a constant velocity. So this only has two forces on it. It's got mg and it's got some normal force. And this guy's got mg and some normal force. Now they come into contact with each other. They are colliding. They're in the middle of their collision. It takes time to collide, but it's a very short amount of time. And during that collision, whatever the forces happen to be, what's nice is we know Newton's third law tells us that they have to be equal and opposite on each other. So there's still the force due to gravity on M1, that hasn't changed. And there's still a normal force, that hasn't changed. And there's still a force due to gravity on M2. And there's still a normal force on N2, but now they're in contact with each other, and so they're exerting a force on each other in the opposite directions. So there's a force on mass 1 from mass 2, but that must mean there's also an equal and opposite force on mass 2 due to mass 1 from Newton's third law. So if we look at the sum of the forces, oh, okay, so wait, and then afterwards, let's just do the whole picture. So afterwards, they go off in opposite directions with some new velocity, v1 final. That's not necessarily the same speed as it was initially and in different directions. This is v2 final. Okay, so this is the collision, then they're going off in different directions. Coming in like this, leaving like that. And then the free body diagram down here is going to be the same as the free body diagram up here, okay? Because if there's no friction, the only thing in contact with them right now is the track. So the sum of the forces here is 0. And the sum of the forces here is 0 for the whole system. If you add it all together, because this force cancels out this force, and the sum of the forces here is 0. How is that going to be useful to us? So the sum of the forces on the system is equal to mass 1 times its acceleration plus mass 2 times its acceleration. But we also know from our lecture and from our lab experiment that acceleration is the slope of a velocity versus time graph. So it's the derivative of the velocity versus time. So we can rewrite that as the derivative of velocity versus time. So the change in the velocity of mass 1 with respect to time plus mass 2 times the change in its velocity with respect to time is equal to the sum of the forces. But now we've got this new definition that momentum is mass times velocity. And as long as we're not losing any mass, this is a constant, so we can pull it into the derivative. So this is the same as the change in time of this quantity, mass times velocity, plus the change in time of this guy's mass times velocity. So we can rewrite that these guys are the momentums. So this is the same as the change in time of the momentum of mass 1 plus the change in time of the momentum of mass 2. Like, how does the momentum for mass 1 change with time, plus how does the momentum for mass 2 change with time? But we added up the forces for this collision, and the only time there are any forces on each other, they're these, but they cancel out because they're equal and opposite. So they equal 0. Okay, so that means we have 0 is equal to, I'm going to factor out this ddt, the change in time of the first mass's momentum plus the second mass's momentum. Now think to your calculus class. When you have the derivative of something and it equals 0, what does that mean about the thing that you've taken the derivative of? What is it? It's a constant, exactly. That means it's not changing as you change the denominator. So that means that the sum of the momentums does not change with time. It's constant, it's conserved. So the momentum of the first mass plus the momentum of the second mass, when you add those together at all points in time, here, 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 anytime afterwards, it's always going to equal the same number. So we can write that for this experiment as the momentum of the first object, the initial momentum, plus the momentum of the second object initially, is always going to be equal to the momentum some later time. The first object plus the second object. To make it more useful for us, let's just expand that back out again, because momentum equals mass times velocity. So now we see why this is helpful. Because we have that mass 1 times its initial velocity plus mass 2 times its initial velocity is equal to mass 1 times its final velocity. And these are vectors, so we get the direction too. Plus mass 2 times its final velocity. Okay, this is the conservation of momentum formula that we can use. So it doesn't even matter that there's non-constant forces or that there's some kind of a collision. If we know how fast the objects are starting, and we know how fast one of the objects is at the end, we can figure out how fast the other object is. So it's useful. In today's experiment, we're going to do two kinds of collisions. We're going to do two objects crashing into each other. We'll do the two little sleds crashing into each other, and then the little sled crashing into the big sled. And then we're going to do an explosion, which is just a collision in reverse, running time in reverse. And for that one, we'll tie two of the sleds together. Maybe we tie the big one and the little one together. That kind of looks like what we do. And then we're going to light the string on fire, and then they'll go flying apart from each other. Because they have magnets. Yeah, they have magnets on them that are repelling each other. Right, so we're going to talk about conservation of energy too. So if you go on Canvas, you'll find the tables, but these are the experiments. So the first experiment is you're going to have the little mass, and it's got the Velcro facing that way, and you're going to start it off with some velocity, v1 initial, we can call this m1. And the second little mass, you put the Velcro facing the first one, but we're going to have it at rest. v2 initial equals 0. Okay, so these are the little Velcro fuzzies. Okay, so they're going to stick to each other. Okay, so let's do conservation of momentum. So initial momentum is m1. Let's make this the positive x direction. So we've got m1 v1 plus 0. Yes? Okay. m1 v1 plus 0. This is the momentum of the second guy. Is equal to, what's the final momentum going to be? They're going to be stuck together and moving with one speed. So the final momentum is m1 plus m2 together, moving at some final velocity. Okay? So we've got, solving for v final, we've got m1 v1 over m1 plus m2 is equal to v final. So if you know the masses of your sleds, and if you know how fast the initial guy is going, then you should be able to predict how fast this guy is going after the collision, what this v final is. And that's the comparison that you're going to make. In order to take the data, you're going to have the tape set up on your air track. Remember all the rules about the air and the sliders and everything like that. So just like make sure nothing is grinding on there. And you're just going to be getting the dots of this one guy. Right? So initially he's going to have, dots that are moving. They're going to be well spaced apart from each other. Will be moving pretty quickly. And then when they become stuck together, you're recording his dots afterwards. So you're recording the whole time. Before the collision, click, 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 click. Collision happens, click, 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 click. After the collision, click, click, click. You're recording the whole time, but you're going to see your dots change. So before the collision, the guy is moving pretty quickly. And then if this was the moment of the collision, now he's going to be moving slowly. But we're assuming with some constant velocity, not accelerating. So the spacing between the dots should be the same in the two different sections. So this is before collision, and this is after. And the collision probably takes someplace around there, sometime around there. And if you read in the lab manual, it says that you should have at least 10 dots or 10 spaces between dots. And remember, the spacing between the dots is 0.1 seconds time-wise. So you'll be able to find your velocities from the total length of 10 dots, so 10 dots, or 10 spaces, 10 dots, spaces. So the V is going to be total length of the 10 spaces divided by 10 times delta t, which is 0.1 seconds. So that's how you get your velocities from today's experiment. So you'll measure the dots 10 spaces worth before and get the velocity then. That's this guy. Then you measure the dots after the collision, and that's that guy. And if you look on Canvas, it'll tell you what you need to compare as far as the percent difference goes. So you do that for the two little guys, and then you do it for a little guy and a big guy, and you take all the data. And then you do the explosion experiment. And I'll talk about the energy after that. So let me make a little space for myself to talk about energy. So this is the first experiment with the two pairs, little and then little and big. And then the explosion you just do with little and big, if I'm looking at it correctly. And in that case, we're starting tied together. This is M1, this is M2, and they're tied together with some string at the top. they're trying to get away from each other like two dogs that are attached to the same leash because there's magnets on there. And we have the polarity flipped so that they're exerting a magnetic force against each other. So they don't want to be tied together. So as soon as you break that string with the lighter, I think is the best thing to do, they're going to go flying off in different directions. So is momentum conserved? Yes, because even though there's a magnetic force on mass 1 for mass 2, there's a magnetic force on mass 2 for mass 1. Newton's third law says they're equal and opposite. If there's no friction, the sum of the forces is 0, and all this stuff holds true, and momentum is conserved. So in the initial momentum, we have 0, because m1 v1 is 0 and m2 v2 is 0. So the only way that this can be conserved is if one guy goes in one direction and one guy goes in the other, because these are vectors. So one could be negative and one could be positive. So if this guy goes flying off in this direction, once they get severed, and this guy goes in this one, using this coordinate system, this guy would be negative. So we've got negative m1 v1 final plus m2 v2 final. One has to be negative, one has to be positive in order for them to equal 0. And then the comparison that you want to do is in Canvas, and it'll tell you how to do the analysis here. Or in the lab manual, because I pretty much just followed that too. So we also want to look at energy, which is different from momentum. And I also haven't talked about that yet in much. It's a scalar quantity, it's not a vector. And we don't have to go through all the details, but I'll just tell you that the kinetic energy is given by the expression 1/2 mv squared. Okay, so momentum is mv, but it's a vector. This is momentum. Kinetic energy is 1/2 mv squared, but it's a scalar, no vector symbol. So it could be, well, this could only be positive actually. Energy could be positive or negative. The kinetic energy can only be positive because the v is squared and mass is not negative as far as we know. Okay, so why are we concerned with kinetic energy? Well, because even though momentum is conserved here, energy is not going to be conserved. So some of the energy goes into the deformation of the Velcro, actually. Because the Velcro is mass, and it has to move in order to make the little Velcro hooks lock around the little Velcro loops, and you don't get that energy back. So it takes some energy to do that. And we're going to try to figure out how much we lose. So, but the V is the same. So you get your V's, all your data you get from the dots, the spacing of the dots. But you're going to want to compare your kinetic energy before to your kinetic energy final. I think we're subtracting. Oh, it's in Canvas. We are subtracting kinetic energy final divided by kinetic energy initial. We're calling this in the lab today this little lowercase f, and if you go on Canvas, there's a prediction for what it should be, and it's in the table M2. So the theory is that it's M2 over M1 plus M2, and M2. So this is only for the sticking experiments. This is not for the explosion experiment. So just for sticking. Okay, so the theory says that the amount of kinetic energy that you lose, which is right here, is equal to the mass that's at rest first divided by the total amount of mass. That's the theory. And this will be the experimental value because you're going to get your V's by measuring your dots. So that's part of the table. And also you'll be happy to see that you don't have to write up a full lab report for this experiment. You go on Canvas, you just fill in all that data in your lab notebook today, you're done. I mean, you take a picture of it and upload it. So easy experiment today. Wanted to give you guys another break. So there you go. Have fun.